Let's review the material that we have seen. So we are discussing about conditional probability. This was the thing that we were discussing. There is some problem with the pen. This is what we were discussing, conditional probability. So in conditional probability, the first important formula that we saw, which I said you should not remember the formulas, but what you should do is you should derive them from the first principles, was this. If you have an event, if you have two events, A and B, and if B occurred, so what you can say is the probability of this, probability of A given that B occurred, is probability of A intersection of B divided by probability of B. Give me a second, I'll just fix this. So this was the first important formula. So in this, I was saying that you are conditioning on this. Okay, this is called as conditional probability. And the second thing that we saw is after this conditional formula, we saw a multiplicative rule. So multiplicative rule was a consequence of this. So in that, what we said is we just want to compute this term. If we want to compute this term, so how can we compute this term? It's a probability of A intersection B is equal to probability of A given B, probability of B. So this means probability that B has happened, probability of A that B has happened, multiply probability of B. So this was called as multiplication rule, and then we also saw a generic form of this. This was conditional probability, and this was multiplication rule. So this over here was conditional probability. This is conditional probability. And then we also saw law of total probability. So in that, what we saw, I told you that if you have a difficult problem to solve, so you should not solve the problem directly. One of the mechanisms is that you should break down the problem into some smaller sub problems, assuming that the smaller problems are easy to solve. So I was making the diagram something like this. I said if this is an event B, if you have to compute the probability of this B, so what you can do is you have the whole sample space S. You break this down, you break the sample space like this, A1, A2, something of this sort, A1, A2, A3, A4. Okay. And then what you can do is if you want to compute the probability of B, you can compute it with this if you have these intersections. So let's suppose we have just two events. If I break it down into two events, A and A complement, something of this sort. So I can write probability of B is equal to probability of A intersection B plus probability of A intersection B complement. So why is this so? Because this B, A and A complement are the events which are disjoint, and I can use additive theorem of probability here. The probability of B, then I can use here again this multiplicative rule. Probability A happened, multiply by probability of B given that A happened, plus probability of let's suppose again I can say that A complement happened. So this should be A complement over here. Okay, probably that A complement happened multiplied by probability of B given A complement happened. Okay, this over here was called as law of total probability. This is law of total probability. And then as a consequence of all of these things, we derived what's called as Bayes' theorem. So Bayes' theorem is one of the very important, very deep results from conditional probability. So it comes from this probability of A given that B occurred is equal to probability of A multiplied by probability of B given A divided by probability of B. So this over here we call this term as prior. This was called as posterior. This over here is called as likelihood. And this is what is called as total probability. Okay, these are the important things that we have seen in the previous lectures. I hope everybody is clear, at least clear with all of these terms that we have written over here. You should be clear, otherwise it will be pretty hard to follow the subsequent lectures and subsequent concepts. Okay, again going through, so we have conditional probability. This is what conditional probability is, and then we have multiplicity rule. I just wrote it for two events. You can extend it for n events, and then I had law of total probability, and then I had Bayes' theorem. I hope everybody is clear till here. So to just revise the Bayes' theorem a bit and see how we can solve different questions and in some different ways. So today I'll again start with a question. After this revision, we'll do a question. I'll give you some time also to solve it, and then I'll show you how to make mental models, how to make pictures out of this so that you can answer the question correctly. The question goes like this. Let's suppose some company is there who's making these radars, and the radar system detects this aircraft, but it's always not perfect. You know that sometimes they can give wrong signals as well. Okay, so sometimes it detects an aircraft where it is not present, so it gives false alarms. Okay, it is like the problem that we have done in this medical test also, where the test is not accurate. So in this also, the radar systems are also not always accurate. So now what is the question being given is, so let's suppose if there is an aircraft, okay, or there's a possibility there is aircraft, or there's a possibility there is no aircraft. If there is aircraft present, so the probability for that is, probability of aircraft being present is 0.05. Okay, so usually that's the usual case, the prior belief. And if the aircraft is not present, that means 1 minus of this. Probability that aircraft is not present is 1 minus 0.05. Okay, that comes out to be 0.95. Aircraft is not present. And then we are saying that detection given that it's present. Let's suppose if we got a alarm, or we got a signal from radar, and the aircraft was actually there. So that means the positive hit rate. So you have true positive. So what is the true positive rate? How can we write that? Probability of, given the radar gave the signal and aircraft was there, so this probability is 0.99. This is very highly accurate radar system. And then we have one more thing, probability that radar gave the signal, or it gave the ring, given that aircraft is not there. So this is 0.1%. That is false alarm was given. These are the numbers that are given to us. Okay, so it's easy to compute. You can just compute these things. If I ask you now compute the probability that you have you have the alarm, but you have to compute probability of A given R. Basically, alarm was there. R basically means the alarm was raised, and A means aircraft was present. So if you have to compute this, given that the alarm was raised by the radar, so what's the probability there is an actual aircraft there? So you can easily use the Bayes theorem, that I think now should be your bread and butter. You should easily have the formula and plug these values in. But I just want you to think in the different ways also. So how can we do it? So you can make tree diagrams. So these are some sort of sequential decisions. So you can do it like this. So aircraft is present, okay, or aircraft is not present. You can do something of that sort, and then we'll see based on that we'll take these decisions. So now let's suppose start from here. So this is our start position. Now there are two possibilities. There is possibility of A and possibility of aircraft not being present. This is A and this is aircraft not being present. And then in this case there are two more possibilities. If aircraft is present, there will be a detection, alarm will be raised, or there will be the case where alarm won't be raised. Okay, two more cases. So again here also same thing. This is the tree diagram over here. So if you see this case, so here the alarm got raised, and then you have to see this. Here alarm was raised. Let's suppose alarm was not raised. In this case, the same thing. Now if you go on to this, so this can be written like this: alarm A was there, that means aircraft was there, and alarm was raised. So this portion over here is where aircraft was there, and this portion over here is where aircraft was not there. So if you see this can be written like this: aircraft is and this event happened. So again this can be written A intersection of R C, that means aircraft was there and alarm was not given. So here this case is aircraft was not there and this was a false alarm. In this case, no alarm, no aircraft, no alarm and no aircraft. So if you see each of this branch, if you see each of the branch in this branch, or if you see this branch, or if you see this branch, or if you see this branch, so all of these things can be seen as multiplicative probability. If you have to compute the probability of A multiplied A intersection R, so you can just multiply this and this. Okay, this is multiplicative rule. This basically this branch over here is probability of A, the probability that there is an aircraft, multiplied. Then this over here, if you see this, so this is probability of alarm given that aircraft was there. So this is that branch. So each of the branch can be computed by multiplicative rule. That is what we have seen. So here if you write it over here, these numbers can be written: aircraft is there and aircraft is not there. So these are the priors I have. So this is 0.05 and 0.95. So this number is 0.05 and this number is 0.95. Okay, and then we have this. So this branch over here. So what is this branch? So this branch says that aircraft was there and alarm was raised. So this is basically this probability given that aircraft was. What's the probability of alarm given that aircraft was there? So for this we can write this probability of R given A, that is 0.09. So this is 0.99. Oops. And again, you can fill in the values for all of these. Now what I said is, the first thing is you can compute this by using multiplicative law, this over here. And one more thing that you have to compute is probability. So you have to compute basically this. You have to also compute probability of alarm, probability of R. Because if you use Bayes theorem, you have to see that this R will come in the denominator. But if you see how alarm is being raised, so it is spanned through the events. So what is the event that raised the alarm? So first event is this. Here it raises the alarm. Over here, it raised the signal. So also here it raised the signal. So now you have to sort of add these things. You have to add this and you have to add this. So basically you have to add this branch. You have to first compute the probability of this, and you have to compute probability of this branch, and both of these branches have to be then added. Okay, that's how you can compute this P of R. So P of R is this thing, and then Bayes theorem can be computed. You just use this multiplicative rule, and then you just use the law of the total probability, and you divide both of these things. So this is one other way of looking at it. So when you are given a process, so you can make something of this sort of diagram, where you make this is called a tree diagram. Okay, not a very hard name to remember because it looks like a tree. So in that, you give these events different numbers, and you use multiplicative law and the law of total probability to compute the two different things, and then you can just take the ratio of those to come to the Bayes theorem. Any questions on it, or was it clear? Now moving on to the conditional probability, we'll introduce some more concepts by using some different examples, and we'll also show how counterintuitive probability is. So one more paradox that we'll take, which we just touched in the last session, was Simpson's paradox. Okay, so what does this paradox say? Why is this paradox even called? So paradox is, as I said, the real paradox is not there. Then when you hear some statement or you hear something, so it feels so counterintuitive. It feels that this is total counterintuitive. But after you dig deeper, so then you have to realign your thoughts, you realign your beliefs. Then you say, oh, this was not the way I was thinking at the first, and you get your intuition right. So paradoxes are where you feel this is intuitively wrong, and then after time of thinking, and you said, okay, this is the problem was with my thinking, not with the way the question was posed. So what is the Simpson's paradox saying? So it's a phenomenon where you can see a trend. So you can see a trend in different groups of data. If you have groups of data, you can see a trend in there. But this trend reverses if these groups are combined. So what is the meaning of that? So let's suppose you can have a possibility where you have a doctor. Let's suppose we have two doctors. We have two doctors. Say Dr. Mahmood, and I think we have Muzaffar, a doctor of philosophy. So but he's not here. So Dr. Muzaffar. So we have two doctors, Mahmood and Muzaffar. So one among the doctors can be having higher success rates in every type of surgery they perform. Okay, but when you see overall the doctor who has the least success in individual things, he have more success rates overall. So this looks so counterintuitive. Like individually, if a doctor has higher success rates, how if we combine them, how can the success rate be more? So this is with the doctor. So there is a one more famous thing. Let's suppose if you have 4 types of these jars in which you have some candies, 2 types of candies. Let's suppose you have red candies and you have blue candies, something of this sort. So red, and then you have these not blue, purple candies. Somebody will call me colorblind for just not taking the right color names. So if you have these jars, so if you pick up randomly one candy, okay, if you randomly pick one candy, let's suppose somebody prefers and so say your preferred candy comes out from this. So it is a very high likely that if you just randomly sample one candy from it, so whatever candy you like, that comes up. Let's suppose if you like red, so the red candy will come out of this, like more number of times. The probability that you will get your preferred candy is more here. And similarly, if you will prefer, if you will take from this, so it will be more here. So basically, what I can do is, I'm saying if you have these 2 jars, so probability of getting your preferred candy from this jar, then this jar is more. That is, you will get more from this jar, or I can write it like this. Okay, probability that you will get preferred candy from this jar is more than probability of this. Similarly, I can do it for this also. I can say probability of getting a candy from this jar, which you prefer, is more than candy, more than this. So now if I combine if I do one thing, if I take these 2 jars and if I combine the candy somehow, okay, I now take 2 jars. So I am putting these candies in this jar and these candies in this jar. What might happen? So what might happen is that now overall when you group this together, so the probability you will get the preferred candidate is less than suddenly. Okay. So doesn't this seem counterintuitive? So for how many people does this seem counterintuitive? This should not happen. Okay, similarly in the doctor's case, I was saying that if there are two doctors in which one of the doctor has always the higher success rate for individual surgeries, if they perform individual surgeries, so he has always the higher success rate. But when you check it on the group level, when you see overall, so what happens is you will see that the doctor who has the less success rate in individual surgeries, suddenly he has more success rate in the overall surgeries. So this also looks counterintuitive, and I think there has been a lot of lawsuits based on this. I was talking about one case was made, lawsuit was made on UC Berkeley. So in UC Berkeley, what the case was is that they said these people are being partial towards women candidates. They in their postgrad programs they don't accept more female candidates. So overall it looked so, but when they checked at department level, so department level things were looking fair. They were saying, oh, we are admitting female candidates, but the overall effect was if they are discriminating between males and females over there. So it was again the typical case of Simpson's paradox. Okay, let's first see it with the doctors, and I'll make some data and then I'll convince you with the data, and then we'll see it from the conditional probability. Okay, first you should be convinced that this somehow looks paradoxical. If it does not look paradoxical, probably your intuition is right. So for the first time when I saw this looked paradoxical to me. Okay, let's see how this happens. So I'll make some table like this. I'll make two tables. So we have two doctors. We have Mahmood over here and we have Muzaffar over here. So two doctors are there, and let's say I'll write name of diseases. So let's say they perform heart surgery. Mahmood performs heart surgery, and let's say some other disease, let's say injection. Pretty easy, not a surgery. So heart surgery and injection, similar cases. And there is success rate, there is failure, there is success, and there is failure. Okay, I'll make sure that numbers for both of these. Sometimes people might feel, okay, if one doctor performs more surgeries, let's suppose if one performs 100 and other performs 200 surgeries, so there is a discrepancy. So I'll make sure that the numbers are right, that each of the doctor performs the same surgery, same number of surgeries. So here if you see in this heart, in total surgery, we'll take 100 total surgeries. So let's suppose the doctor first, Mahmood, he does heart surgeries. So he is success in 70% in 70 cases, and he's failed in 20 cases. Okay, and then let's suppose he does this injection. So in this he does let's say how many, 10 and 0. Okay, the total surgeries he performed was 100. 70 plus 10 plus 20 was 100. So in the injection case he never failed, pretty good doctor. So in heart surgeries, difficult surgery, so out of 70, out of 90 he failed 70, he succeeded 70 times and he failed 20 times. Similarly this doctor over here, so he performed heart surgeries, let's suppose 10 heart surgeries, and he succeeded let's say failed 8 number of times and succeeded 2 number of times. He looks pretty bad given from this situation. Or again right here, so let's suppose if he performed injection surgeries, so let's say in total he performed 90, so in 81 he succeeded and in 9 surgeries he failed. So if you see over here, if you now compute, if you see the success rate of the doctor for individual surgery, so success rate over here is 70 divided by 90, okay, for the heart rate, and success rate over here is 10 divided by 10. In total he was successful all the time. So in here if you see success rate, if you succeed, this is 2 by 10, pretty bad. 2 by 10, and then if you see this success rate for this, so this is 81 by 90. So I'm just calculating these numbers. I think I have these numbers written somewhere. So for the surgery one, for the surgery, heart surgery, so Mahmood is successful 77.78% times, and here he is successful 100% of times. Okay, you can see that Mahmood is better in heart surgery as well as in injection. So in the second case, if you see Muzaffar being 20% having 20% success rate in heart surgery, and he has here 90% success rate. Let's suppose we consider this 90% success rate. So if you see in both of the cases, in all the cases over here, you can clearly see that Muzaffar is not a good doctor, but Mahmood is a way better doctor than Muzaffar. So giving today benefit of doubt to Mahmood because Muzaffar is not here. So now if you see this, so this is in the individual surgery. If I now combine the result together, if I combine them, So if I combine the results, combine results. So now total successes. How many successes did this doctor had? He had 80. Mahmood had 80 successes and 20 failures. So he was successful 80% of times. Okay, but if you, this was for Mahmood. If you see Muzaffar, so Muzaffar was successful 83 times. 81 plus 2. He was successful 83 times, and he failed 89. He failed 17 amount of times. That is 83% success rate. Okay, so you see, for each of individual surgeries, Mahmood was doing better. So, but when we combine the results together, you saw the success rate of Mahmood dropped to 80%, and but Muzaffar had 83%. So now you can use this as an ad also. So you can use it that I perform better surgeries. I have 3% more probability of getting a surgery done than this doctor, and I'll maybe charge you less. So doesn't this seem counterintuitive? So in here, what we saw is that individually the doctor was better in all the possible surgeries in the world. I just took the example of 2 surgeries. Okay, so the problem here was the doctor Mahmood was performing harder surgeries. Okay, and he was failing sometimes. So here the Dr. Muzaffar was performing more easy surgeries. So in that case, he was still having some failure rate. So usually this happens if you have a case where there is a very good doctor and he is performing very hard surgeries. He's usually having less success rate. Okay, what I was telling you about that, the Simpsons paradox is always used by these marketing agencies or these ad people. They'll show this much success rate, but because the bar is too low, because the tasks they are doing, because numbers can manipulate in such way, and they can write it like this: we have this much success rate, we have this much. Let's suppose it can be also done by coaching institutes. If they take brilliant students, they only have entry to, they initially take students where they ask them to give the test, and once they have that bar cleared, they say, okay, this student is very brilliant, and now we have very high probability of this getting successful. Then we say our success rate, then they say that our success rate is 90%. But you have an advantage, clear advantage, because the students that were in your coaching institute were way better. They were very better from other people. And if you have an institute where you get the students who are of average quality, and then these people cannot publish that we have success rate of this getting into competitive exams. So this Simpsons paradox is used everywhere. Now you should be refining, filtering all these ads, all these claims by using Simpsons paradox. You should be having this doubt whenever you see an ad, when you use something, when you see numbers per se. If somebody is claiming something, so you should probably see that is their bar too low, and are they coming up with the numbers so that overall thing favors them. Okay, so this is one more thing in process. I told you in probability we'll not just learn to compute stuff, so we'll learn basically to think. So in Bayes' theorem we learn to think how to update probability. So in this Simpsons paradox we saw, okay, how can the brain be hacked, and how can we sort of refrain from doing that. How can we easily catch that mistakes if somebody is using the Simpsons paradox? Because the bar is too low. The simple, if somebody wants to write this Simpsons paradox, so they will say you keep bar too low. Bar is too low, and then you can come up with the numbers. So it comes in baseball. So if the player was having higher batting average in, let's suppose, in first half of the season and in the second half of the season overall, but he has lesser batting average than overall. So all of these things can be dealt in this. Okay, so now let's do this conditional probability treatment of on this. So first we'll define these events. I'll make it more generic. I just took an example, extreme example, to justify the case, and then how can we use the conditional probability on these things. So for the conditional probability, what we basically do is, the first step is, in probability in general, we define the notation. Notation is very important in mathematics. So if you define notation, and then the things become easy. As I always reiterate, it becomes easy to perform calculations and algebra on the notations rather than having some sentence which is written very verbosely. It becomes difficult for human brain. So let's now introduce some events. Let's say D1 and D2 be 2 doctors. Now I'll just abstract or detail. That's what mathematics does. So mathematics sees a real world problem. It sees, okay, this is a problem. Let's create a template, abstract or detail. There are a lot of problems that fit into this description. So let's abstract out all these details. These details are irrelevant for me. So I'll just introduce symbols and do it. So if somebody do a problem, so he'll just fit this template in that problem. That's what we'll be doing now. So we saw something on one problem, and we also saw instances where this problem is applicable. There will be a lot more cases than this. You saw doctor case, you saw UC Berkeley's case, you saw we can have ads, and we can have a lot more examples in this. Now what we're trying to do is we're trying to abstract out the details. That's what a mathematician does. Okay, now we will say D1 and D2 be the doctor. Okay, if D1 be the first doctor that we have Mahmood, and D2 be the doctor we had Dr. Muzaffar. And then we'll say S is the event that surgery is successful. So S is surgery is successful. I'm just verbally telling you, and I'm not writing them down. So then I'll also define F is failed surgery, or I can say F. We can have introduced quite less symbols also, but I'll try to introduce more symbols. So S is success and F is failure. And then we have surgery V1 and V2, the value type 1, value type 2. So I could have only done it with 3 symbols, but I tried to bring in more symbols. So I could have only done it with 3 symbols: doctor, success, and type of surgery, something of this sort. So doctor complement is, so if this is Mahmood, doctor complement means this will be Muzaffar. So surgery, if this is success, surgery complement will be failure. So if this was T, type of surgery, if this was, let's suppose, heart surgery, and this will be injection, if I write T complement. You could also done it with this, but introducing some more symbols can make our job easy, but it is equivalently valid on this also. Okay, sometimes people try to introduce less symbols, and that you should also do it. Why? Because sometimes it makes more sense. So now we want to analyze this problem conditionally. Probability of success given DI. So probability of success given that DI, given the doctor 1, the total successes by doctor I divided by total number of surgeries performed. So this is total or number of surgeries by D1 or DI divided by total number of surgeries by DI. This is what we want to compute, and then what we have to do is we'll condition it. So here we initially condition it success given the doctor, and then second case is we'll condition probability of success given doctor I and surgery, let's suppose J, V1 or V2, and this is what we'll condition. So this will be successes of doctor I in surgery VJ, success, number of success of doctor I in surgery VJ, which we represent by VJ, and then divided by, we'll say total number of total number of surgeries by DI in VG. Okay, total number of surgeries which they perform. I think this is not visible over here. Total number of surgeries by Dr. DI of type VJ. This is what we want to compute. We are saying that probability of success given that doctor has performed surgery, and the probability of success by Dr. VI given that he's performing VJ surgery. Okay, these are the things that we want to compute. Okay, now if you see these two things, okay, now what might happen is, you can, if you compute this thing first, if you compute probability of success of doctor 1 comma on surgery 1, it will seem to be greater than probability of success of doctor 1 doctor 2 on surgery V2. Okay, this will on V1, sorry, on V1. Again, for same probability of success given that doctor 1 is performing the surgery on surgery V2 will be greater than probability of success given that the doctor 2 is performing surgery on V2. But if you see overall probability of success given that doctor 1 is performing surgery and probability of success given that doctor 2 is performing the surgery, this sign will flip. Okay, this is where the magic comes in. So I am always telling you, read the equations as if you are reading English, as I am reading it right now. So probability of success given that doctor 1 has performed surgery V1 is greater than probability of success given that doctor 2 has performed surgery V1. Similarly, probability of success given that doctor 1 has performed surgery V2 is greater than probability of success given that doctor 2 has performed surgery V2. So in both the individual cases, you see that the success rate for this is more. But when you suddenly combine them, probability of success given the doctor V1 is less than probability of success given the doctor V2. So you can fill in all these computations that we did. So here you can easily compute it by using conditional probabilities. There is no difficult thing in this, but I wanted to take your attention over here. So you see individuals, in individual cases you had this sign. So you had always a greater sign. So but this sign suddenly flipped. Okay, so this is the generic case of Simpson's paradox, where you have something of this sort, you have individual groups. So where you see some trend. That's what I said in the initial thing. I said there is a trend in the individual cases. It seems that there is some trend, but this trend reverses or it does not follow. Here you can see it clearly reverses. The trend reverses over here. So the trend was this initially. So when we aggregated this thing, when we combined them together, so the trend almost reversed. Not almost, it reversed in this case. But sometimes it may happen the trend is not following anymore. It might not reverse all the way, but this is the generic way of Simpson's paradox. Any questions on Simpson's paradox? So now we'll move to independence. So in probability theory, events can be either dependent or independent. So we'll see what is the meaning of dependent first. In general, what's the meaning of dependent? So if you see, dependency is created when, let's suppose, if I am not in the class, so you people, nobody, let's suppose, among you can teach other people, so there's a dependency created on me. So if I came, then something will happen. So there is a clear dependency. Or in the similar fashion, if one thing has an effect on other thing, so there is some clear dependency. So if this thing, if something happened in one thing, there is something happening other thing also. So that means there is a clear dependence. Okay, so that's the meaning of dependence. In general, we see dependence like this. So what's the meaning of independence? So independent means, so if you are doing an assignment, if I am doing an assignment, so my doing assignment won't probably have any effect on you. So that means independence. But usually in the world, you will see a lot of dependencies. So in the last lecture, as well in the last session, at the last moment I said, so our decisions are mostly dependent. So whatever company you are in, so if your friend takes a decision, it impacts you somehow. But we have also a lot of independence also. How? Let's suppose if you do not know a person and he is doing something, so probably if you just see it in granular way, it seems like it is independent, but maybe it is dependent. It is coming from person A to person B to person D and to you. But most of the cases you will see in the world, if you have something happening in Mars, okay, and if you take those suppositions and all these things out of the equation, you will see that a lot of events they are independent. So one thing happening of one thing does not impact happening of other thing. So that's what independence means in this. In the context of probability, two events are said to be independent if the happening or not happening of one event is not dependent or happening or not happening of the other event. Okay, so we have two events, say event B, A and event B. So these are two events that we have. So I give the real world example also. So as I said in one of the example, if we have a match between India and Pakistan, flying of an aircraft in the initial ceremony has nothing to do with that Pakistan will win. Okay, so these two events will be independent events. So if we have event A and if we have event B, so an event A is not putting any effect on event B. If event A happened, so nothing, we can say nothing about event B. If event A does not happen, we can still say nothing about event B. Basically, happening of event A gives no information. Okay, happening of an event gives no information. So why am I saying no information? Because as I said, probability is dealing with uncertainties. We were uncertain about A and B. Now A happened. So if somebody says me what happens to B, if I am in a position to say that happening of A gave me no information, it did not increase or decrease my uncertainty, it said nothing about event B, then I'll say that this A and B are independent. How can we write this? Probability of A given that B happened is still probability of A. That is, initially I had some prior about B, I had some prior about A. Now let's say this, I have written in the reverse because I explained it in this fashion. The probability of A happened given B is still probability of B, because happening of A does not give me any additional information about B. So that means I'll call these events as independent. They have no connection to each other. So as I said, if you toss one coin, okay, and then if you toss second coin, so if in the first coin, if head appeared or tail appeared, it doesn't affect what will happen on the other coin. So it might be tail, it might be head, doesn't matter. Okay, so these two events we'll call such events that is independent event. In these in the two cases, we'll say A and B are independent events if happening of A gives no information about happening or not happening of B. It gives no information. It basically does not update my belief about B. So my belief about B remains the same. That's what I said. So if probability of B given A, so I had some prior belief was probability of B. This was my prior belief. So somebody gave an evidence. Somebody gave an evidence that A happened. Now this evidence was irrelevant to me. This evidence gave no information about B. So what I can say is, so given an evidence which is irrelevant to the situation, I can say that if my prior got no updates, this prior was not updated, I'll call this event A and B as independent events. Okay, so putting it mathematically, so people usually write it like this: if we have probability, if we have P and B happening of these two simultaneously, this is equal to probability of A, probability of B given A. Okay, so this is by multiplication rule. So this is probability of A, and now if this is independent, so I can write it probability of B. So usually in the books this is introduced like this: probability of A and B is equal to probability of A multiplied by probability of B. Why is it written so? Because this definition has some clear advantage. So this definition has some problems. So this, if you use this as a definition, it has, I won't say problems, but it is a bit restricting. So what is the restriction? The restriction is that here probability of A can't be 0. Probability of A should not be equal to 0. Okay, otherwise this whole thing won't make sense. So here if the probability of A is 0, this becomes 0. Still this definition holds, so it has some advantages. Okay, so that's why people usually use this definition for conditional for this independence. Okay, so clearly this definition comes from here. So this is the law of, this is multiplicative rule, this over here, this is multiplicative rule, and from this I just substituted this, and I got this. So if you have to now prove two events are independent, what you can prove is you have to prove this, and then it will be clearly that these two events are independent. Any questions on this definition? Any questions?
Hello, sir.
Yes, sure.
Sir,
so if you see this, the question asked was, why do we even read dependence or independence? Okay, the first thing that I will first address is this. So sometimes you have something happens. Let's suppose this A happens. So it can impact B. Okay, this is called cause-effect relation. So you have A, and if A happened, B may or may not happen. So this can produce an effect on this happening of A, produce an effect on B. So this is called cause effect. And then you have inference. And if somebody told you now, if somebody said, now this A happened, let's suppose somebody said that, now what is the probability of B given this A happened? Now he is inferring, inference. This is what you do in the machine learning. You have data initially, so you somehow believe that if I featureize the data, if I just tell you the feature of the data, so I had some data with me. So what I do is I extract some features. I extract the features. And now I believe that these features somehow have a cause and effect relation on the prediction. Okay, so we have features and we have the prediction. So these features are assumed to have some cause and effect on the prediction. And then what we say is, now these features happen. Given that you have these features, what is the probability of this class? What is the probability of this? Then you make a prediction. So this is inference. So you can clearly see that sometimes it might happen that one feature that you featureize, that you when you perform feature engineering, when you extract the feature, it has no effect on the prediction. So that time you can see that having this feature happening of this is of no use sometimes. Okay, because if I have this in the data, so this doesn't make sense for this. Let's suppose if you have, I'll make a very simplistic example. So if you are detecting if somebody has a brain tumor or not, and let's suppose you are also having a feature in the data how long his or her nails are. This looks irrelevant. But because I can name it, it looks irrelevant. But in machine learning, features sometimes cannot be named. They are almost latent, and sometimes you try to have as much data as possible so that you don't miss any cause and effect relation. You don't miss anything that affects that affects the prediction. So if I also take what is the length of nails, so and if I'm detecting tumor of somebody, so maybe there's a very high chance that growth of nails won't affect the tumor in the brain. Okay, and then we can say that this feature doesn't make sense. The feature this they have this independent on the prediction. So prediction and the feature, this is independent. It's not affecting. So I hope your question got answered. The question was, why do we study this? Let's give some examples of independence. The first example I gave: if you have two coins, if you flip these coins, if you flip first coin and if you flip second coin, if we have flip 1 F1 and if we have flip 2. So if we assume that they are not linked with magnet or they don't have anything inside them, if flip of this came out to be head, and here we can also have flip of head or tail is equally likely again. So nothing affects it. Okay, you can see that these two events are independent. One happening of one flip does not give us any information about happening or not happening of event 2, or does not change our belief about happening of F2. Okay, similarly, if you have, let's suppose, die, if you have, let's say 6 dice numbered from 1 to 6. Okay, if some number came up on this, so let's suppose 1 came up on this, so now we got an information. Now this won't update our belief on what will happen with the second die. It's again independent. This is 2 dice example. So there are a lot of events in real world which will have this sort of scenario where happening of one event won't have any effect on the happening or not happening of the second event, or in general happening of one event will give you no information about happening, will give you no additional information by the help of which you can change the belief. So basically in conditional probability, what we saw is happening of one event was giving you some information. It was revealing some information. It was revealing you some information, and then you were updating your belief, because I said conditional probability is a way of thinking. So you have some belief, you get new evidence, you update your belief. Now sometimes you have a belief and you got evidence, and that evidence is irrelevant, and you cannot update your belief with that evidence because you are saying that these two things are not relatable. So that is where I'm chipping in this independence. Okay, let's do a famous problem, and then we'll come back to some more usual questions. So this problem is called as Newton-Pepys problem. So Newton-Pepys problem. So there was a guy Pepys, I think in some era, I think end of 1690s. I don't remember exact date, 93 or something. So Newton and Pepys. So this Pepys was the guy. So he formulated a problem. So and he betted something on that problem. But in order to be sure he couldn't perform calculation, he sent that problem to Newton. He asked Newton, "Can you tell me the probability of these things?" Because he has betted. So I'll tell you the problem first, and then we'll have more discussion. The problem goes like this. So he said, "What is the probability of getting at least 1/6 if I roll 6 fair dice?" Okay, probability of getting at least 1/6 in 6 rolls of die, in 6 dice, and assuming that all of these are not connected, some of they are these events I can assume independence between these dice. So this is the probability of this. And second thing was, so this is 1 and this is 2. The probability of getting at least 6 sixes, or at least 2 sixes, I think 2 sixes. I'm reading out the problem. So probability of getting at least 2 sixes in 12 dice. Okay, and the third case was probability of getting 3 sixes. Oops. Probability of getting 3 sixes in 18 fair dice. So all the dice were fair. This is third thing. The probability of getting at least 1/6 in 6 dice, probability of getting 2 sixes in 12 dice, probability of getting 3 sixes in 18 dice rolls. Okay. So what Pepys said is, Pepys was betting on this possibility. He said, "I'm betting on this possibility. Now, can you mathematically give me an answer? So should I change my bet or should I remain with my bet?" So if you are asked to guess, let's suppose I'll ask you this question. So without using the tools of probability, if I ask you this question, so which thing will you bet on? So what do you think, which will have more probability? So on the random guesses, so some intuitions were saying that answer should be 3, and some people were saying 1, and some people were saying 2. Okay, and let's do a probabilistic treatment of this. So we can do this problem in many ways. Okay, and that's what Pepys was. They sent this problem to Newton, and Newton made the calculation, and we'll make the same calculation what Newton made. Okay, so what did we'll first start with the case 1. So we'll make it in 3 cases: case 1, case 2, and case 3. So I have numbers written over here. I'll directly see numbers from there. So case 1 is this. So probability of getting at least 1/6 in a die. So it's easy to perform the complement. So it basically at least 1 dice was meaning I'll take union of all these things. But if I take the complement, I'll say 1 minus of this 1 minus probability that I'll get no 6s. Okay, probability of no 6s. Okay, now I'll assume independence. Each of the dice is independence from one another, so I can multiply them. So I'll say this is probability no 6s basically means I have 5 non 6s divided by our total 6s. But how many dice do I have? 6. I'm saying 5 by 6 multiply 5 by 6 multiply 5 by 6. So that is probability of getting no 6 in any of the dice. So that this is the probability. So I'm saying 1 minus. That means probability at least you will get 1/6. Okay, so what is this? I think this is 0. So this is 0.665. Everybody understood this? So I'm saying we have to calculate the probability at least 1/6. I'm saying if I have to compute at least 1/6, I have to use the union. I can use inclusion exclusion principle also, that we have done. But the easiest way should be, I can say I'll do the complement of it. I'll say 1 minus probability of no 6s. Okay, that means 1 minus probability of no 6 basically means probability of at least 1/6 in 6 rolls. So what is the probability of non 6s? That is 5 by 6, because we have in total 6 numbers. The probability of non 6s, because 6 is only 1, 5 by 6 is non 6. So for how many, for 6 dice, because I am thinking now the 6 dice is independent. So 5 by 6 multiplied by 5 by 6 multiplied by 5 by 6, that is 5 by 6 raised to the power 6. This is 1 minus 5 by 6. Everybody on the same page? Did you understand? Now you saw this, that we had the probability this much. So this was pretty easy case. Now case 2. Case 2 is probability of getting 2 6s in 12 dice. Okay, now we can also flip this. So we can say this can be also done, probability of at least 2 6 can be also done by inclusion exclusion. You will have to make events like that, but it becomes a bit harder to calculate that way. but you can still calculate that way. It's not the case you can't calculate. So here again we'll do the same thing. We'll say probability of 1 minus, we'll do the complement, probability of let's say no sixes and minus probability of 1 6, at least 1 6, not at least exactly 1 6. So probability of no sixes and 1 6. So we'll compute these two things and then we'll subtract it from 1. Okay, let's do it. How can we do it? We'll say probability of 0 sixes, probability of 0 sixes. So what's the probability of 0 sixes? So 5 by 6 to the power 12. Okay, because we have 5 non sixes, 5 by 6, but we have 12 dice and each of these rolls are independent. So this is probability of 0 sixes, and then we have the probability of 1 sixes, 1 6. How much is that? So we'll say that one among the 12 dice is having 6 on that, and other 11 has no sixes. So 1 by 6 for that one die. Okay, 1 by 6 raised to power 1 multiplied by, and then we have 5 by 6 to the power 12 to the power 11, because one die has 6 on it and other has just non 6 on this. So other non 6 5 by 6 raised to power 11, and on the die which has 6, so it has 1 by 6 probability. But how many such arrangements can be there? There can be 12 possibilities. Okay, because we have these 12 dice, any of the 12 dice can equally have this, that we can take any one among the die and have 6 on it, and for the rest of the 11 dice we can say there is non 6 number on this. So this, I think this calculation comes out to be 0.1122. calculation can be wrong, I don't know, and then this is 0.271. Okay, now if I say probability 0 6 or 1 6, okay, so I have to just add these two things. These two things come out to be 0.3832. okay, and then the probability is 1 minus 0.3832. so this probability comes out to be 0.618. okay, initially what was that? So this was 0.665, this was 0.618. everybody understood the second case second as well? How many of you understood case second? Okay, so we had to compute the probability at least 2 sixes out of the 12 dice rolls. So what I said is it can be computed by inclusion exclusion principle, but what we can do is we can say 1 minus probability of 0 sixes, probability of 1 6. okay, and now we'll do it for the same case 3. Case 3. So case 3 was, what is the probability that you will get I think 6 rolls. Let me see. Yes, probably no 3 sixes. Probability of getting 3 sixes in 18 rolls. Okay, if you roll 18 fair dice. So in that what we can do is we can again say 0 1 2. I'll make it generic. I'll say 1 minus. So what I can do is probability of 0 or 1. I can just make it a summation term. I can say probability of something like that. I'm doing a summation term. So I'll say k goes from, let's suppose, 0 to 3, or it can be 4 5, whatever. I'll make this a generic statement now. So probability of this. So now for these k goes from 0 to n. So for n of such rolls, okay, let's suppose for n of such rolls we can have a 6, and for n minus if we have, let's suppose, n dice, I should give it k, I should say I goes from 1 to k. So for n we have to, in total, let's suppose we have n rolls now. So I'll just make the problem more general. I have n rolls, so out of n rolls I want k sixes. In this case I want, out of I think 18 dice, I want 3 sixes. So I'm saying now I goes from 1 to k. So now on the k dices I want 6. If I want 6 on k dice, the probability should be this much. For the others n minus k, I should be having non 6. So that means 5 by 6 n minus k. For the other n minus k rolls, I should be having 5 by 6. That is a non 6 number on that. But how many combinations how many possible combinations are there? But you have to choose basically k. So how can you choose? You have to n choose k. This is a generic formula. Okay, and this is called as binomial coefficient. We have seen, I think, counting in detail. So this shouldn't be a problem for you people. So how many of you understood this part? So I said let's make the problem general. If we have n rolls, and if among those we have k rolls for which we have to have 6, I said let's make it general. We'll say 1 minus summation of all of these things. So I'll say I goes from 1 to k. If I have to choose k things, I can choose 1 minus 0 sixes, 1 6, 2 6, 3 6 till k sixes. Okay, so 1 by 6 raised to power k means on the k rolls we want to have a 6. So this is the probability. And for the other n minus k, I want to have a non 6. That's 5 by 6 minus n minus k. That means the probability of getting a non-6 on n minus k row, this much this, but I have to have also have how many ways can I choose these k combinations. I can choose it by n by k n c k combination. Okay, now I can solve this. So I can just expand it for 0, for 1, for 2, and then I can evaluate the values. I think the value comes out to be 0.597. Okay, so in case I'll just write case 1, case 2, and case 3. Case 1, case 2, and case 3. In case 1, the probability was 0.665. In case 2, the probability was 0.617. And in case 3, the probability was 0.597. The people who said case 1, this is what Newton proved actually. Okay, Pepys was putting bet on this. So once he sent the letter to Newton, and Newton gave this answer, and he had to change his bet, and because this was a calculation performed. But on top of that, Newton gave an intuition. So Newton gave an intuition for this problem, but the intuition was it was straight away wrong. Okay, so because people afterwards saw their intuition and wrote a lot of proofs that this intuition is wrong. Okay, so why was the intuition wrong? So whatever I know is that Newton never took the assumption that if the die is fair or not fair. So the intuition was based on this condition. The assumption was taken. Nothing was said about if the die is fair or not fair. If the die was made, let's suppose, unfair, then these probabilities will change. But Newton's intuition was not giving nothing about die being fair or not fair. So that people straight away rejected the intuition. He got the intuition wrong, and people have formally proved it also that intuition is wrong. But the calculation was correct. The Newton had performed calculation correct, but his intuition was wrong. So that gives you the thing that intuition can be wrong. So you can also be wrong in intuition. So probability did not seem intuitive to Newton as well. Okay, and one more thing that I can say over here is, so this problem was sent to the Newton in 1690s. So till that we have not. This was initial days of probability where the framework was still getting developed. Okay, and you need a genius like Newton to solve such questions. Okay, now if you just take a probability course, or if you just read some books, you will be able to easily solve such questions. Okay, that is the power mathematics gives you. Okay, so now we will shift our bet to this. So you should shift your bet to this, and this should be pretty easy to compute. So why did I introduce this problem? Because here we assumed independence. So in these die rules, I assumed independence. I could have done it with also with inclusion exclusion principle. Okay, the calculation would have been a lot more tedious than this. So here I just assumed that these dies are fair and they're independent, and I made these calculations. Okay, any questions on this? So we had started about independence. Definition that I wrote is like this. So P of A given B was equal to P of. It basically meant if there are two events which are A and B, and if somebody says that A happened, it gives you no information about happening or not happening of B. I said in conditional probability, what do? You have some evidence, you update your belief based on that evidence. But now if something happened, if you saw an evidence, but that evidence was irrelevant. By irrelevant I mean now you cannot use that to update your belief. So your prior is equal to your posterior. So nothing happened. So this is your prior, this is your posterior. And now I said this definition somehow restricted you. So what you can do is you can write a definition like this. Probability of A and B equal probability of A multiplied by probability of B. So I said this is the definition that we will use for independence. Why? Because it allows you to use probability of A is equal to 0 as well. Okay, so this is the definition of independence. Now we'll see if you have to prove, let's suppose some events are independent. How can you prove? You just have to do one thing. You have to compute the probability of these two events happening together, and then probability of these two and multiply them together, and you see what is the answer. If these two things came out to be similar, you say that probability you say these two events are independent, otherwise they're not independent. This is the mathematical way of proving independence. Intuitive ways, you should feel that if I have information about one event, it gives me no information about other event, that means it's independent. But sometimes the intuition is, to counter the intuition is pretty hard. So what you should do, you should resort to the mathematical notion, and you should go and see. Let's start with the question. The question goes like this. So suppose you have you are tossing two fair dice. Question: you are tossing two fair dice. Okay, let's I'll also introduce some symbols. So E1 denotes the event. The sum of the dice is 6. Okay, you are just seeing the top face of these dice. So E1 is the event that the sum of the top faces is 6, and we have another event which is F. F denotes the event that first die, the top face, the first die is 4. This is 4. First die. First dice is 4. So now you have to tell me, are these two events independent? I'll give you some time because I told you the definition. You have to compute this and you have to compute these two things separately and then multiply them together and see if they are equal. If they are equal, they are independent. If they are not equal, they are not independent. And then you should come up with the intuition as well. Now, in order to compute if these two events are independent or dependent, we'll resort to the definition of independence and we'll see this. Now, we have to compute probability of E1 intersection F, because we have to see that if E1 is independent of F or they dependent. We have to see that. We have to see if this thing is equal or not equal to probability of E1 multiplied by probability of F. So computing this is pretty easy. Probability of E1 intersection F. You'll have to see all the events, all the outcomes in which the sum of the dice is 6 and then the first dice roll is 4. So what is that? So that is 4 and 2. This is the only way possible. Our total outcomes are 36. So the probability of this is 1 divided by 36. Okay. And now computing probability of E1. The probability of E1 is sum of the faces of these dice should be 6. So what are the possible outcomes? So the possible outcomes are 1, 5, and then 5, 1. Okay, I'll just write it reverse as well. 2, 4, 4, 2, 3, 3. These are the 5 events possible in which you have the sum of dice is equal to 6. Now this is 6 by 36. Now you also have to compute probability of F. Probability of this is 5 by 36. Okay, now probability of F is equal. Probability of F, what's the F? F is the first die is 4. So this is 6 by 36. 1 by 6. Probability of F means the first die, the first roll. So this probability of F is equal to 6 by 36. So this means that you have got probability of this F. F is the first dice roll is 4. So first dice looking be 4, and the second can be 1, 2, 3, 4, 5, 6, anything. So that means the total possible outcomes are 36. And what are the favorable? That means 6. So you have 1 by 6. So now you will have to see from the mathematics probability of E1 intersection F is equal to or is not equal to probability of E1 multiplied by probability of F. If you here see, this thing is clearly not equal to. Okay, if you multiply these things, this thing, if you here see that probability of E1 intersection F, this is 1 by 36. 1 by 36 is not equal to 1 by 6 multiplied by 5 by 36. Not equal to this. So clearly these two events seem to be dependent. Okay. Now let's try to build an intuition. Why is it so? Why is it so? So I'll tell you intuitively why does it happen. So now because the sum is 6, so you have to bring sum is equal to 6. Okay. And now somebody told you that 4 has occurred in the first die, 4 has happened. And you are left with this possibility 4, 2, because you are forced now. The sum should be 6, and you are now forced that the first die is 4. What should be on the 6? So now there is only one possibility that 2 should be on the second die. The happening of this 4 gives you additional, it somehow removes other possibilities. The other possibilities that we earlier had, we had other possibilities like 1, 5, 5, 1, 3, 3. So these possibilities are removed by happening of this event. So happening of this event F, this is the event F, happening of the event F. So the first roll is 4. It gives us additional information that how can this 6 happen now. Now you can see that once it gives us additional information, we have to update our belief. So happening of event F gives us some information about event E1. That means these things cannot be independent then. Let's now rephrase this question. Let's say E2 is another event. E2 is an event where the sum of these dice rolls is 7 now. Sum of the faces of these dice rolls is 7. Another, let's suppose F is the same event, that the die that happened, the first die has 4. For the roll, when we rolled the first die, the face came out to be the 4. So tell me, are these two events dependent or independent? If you see these two events, the event E2 was defined that the sum of the faces is 7 now, and event F was kept as same, that the first roll is 4. Now we have to compute, are these two events dependent or independent? It almost seems the problem that we have earlier done, but let's now do the mathematical treatment of this. We'll do it as we did the earlier problem. We'll have to compute probability of E2 intersection F is it equal to probability of E2 multiplied by probability of F. If you compute this, so this says that sum should be, this over here says that sum should be 7 and the first roll should be 4. The first roll is 4 and sum should be 7. This is 3, 4 comma 3, the possibility. Okay, I hope that everybody agrees on this. 4 comma 3 is the only possibility where sum is 7 and the first roll is 4. The probability of E2 intersection F is equal to 1 divided by 36. Okay. Now if you see probability of E2, the probability of E2 is telling me that sum should be 7. So sum should be 7. How many outcomes are possible where sum is 7? This is 1 comma 6.
4 by 36.
How many? 1 by? Is somebody directly computing this? This is 1 by 6. This is 1 by 6. Yes. So there are 6 events where the sum is 7, because you can see that those diagonal elements. So now probability of F is also 1 by 6. Now if you compute probability of E2 multiplied by probability of F, this comes out to be 1 by 6 multiplied by 1 by 6. So this is 1 divided by 36. So you can now see that probability of E2 intersection F is equal to probability of E2 dot probability of F. That the independence is holding here. So you can clearly see these two events are independent. How is it possible? Okay. Now I'll prove something to you. Let's suppose if we have this event E and we have event F. If these are two events, and if E and F are independent, so by independence I mean probability of E F is equal to probability of E multiplied by probability of F. So whenever I don't write something, it means intersection. If I put comma, so that means intersection. This is these are two events. If these two things are independent, so I am claiming that E intersection E and F complement, E and this F complement is also independent. So if E and F are independent, if E, write it clearly, if E and F are independent, these are independent. So this implies that E and F complement are also independent. Okay. Now here what I'll show you how to prove things mathematically. Okay, now you can come up with the intuitive definitions, you can prove it intuitively, but how to prove things. Okay, now the thing is, you have been given this and you have to prove this. Now how to put it in a mathematical notion. So whenever you have to prove something mathematically, one of the skills is to mathematically show, okay, this is given and this is what I have to prove. This is one of the skills. So here it is pretty easy. So given to me is this. So when something is written in words, if E and F are everywhere, I can write given to me is probability of E and F is equal to probability of multiplied by probability of. This is given to me. So what I have to prove? So to prove is this. Now this was given to me in verbose in English statement. Now I am trying to convert them mathematically. So to prove is this: P of E and F complement is equal to probability of E multiplied by probability of F complement. The only thing, why am I proving this? Otherwise, to prove these things is not necessary. You can do it on your own. I just want to show you that how to think mathematically. How can you put this verbosity or something written into mathematics and then try to reason it from mathematics. So this is given to me because the given is that these things are independent. This is given to me. So I should somehow use this result so as to arrive at this result. So this is what I have to prove. Okay. Now how to do it? So I have to somehow bring this F complement into the picture. Because I have E and F, somehow I should be able to bring this F complement in the picture. So if you see, we have made a lot of Venn diagrams. So in those, what we said is, I said if this is our sample space. Oops, this is our sample space. If these are two events, one is E and one is F, something of this sort. So this is E and this is F. How can I represent this E? So this E over here, this event E, how can I represent it? I can represent it in two disjoint events. So I can represent it with this part, that is only E basically, and then I can also represent it then plus this, the intersection part with this. So I can write this E in this fashion. So I can bring F complement, because in the thing that I have to prove, there is this F complement. So I'll have to bring this F complement somehow. So I'll say this event E. So this event E can be written as E intersection F That means this part, this yellow part, plus E intersection F complement. Okay. So what I am doing is I am doing E intersection F, that is this portion, and E intersection F complement, that is this portion. F complement is everything that's outside F. So that leaves this intersection part is equal to this part. That is the red part, and this is red part, and this is yellow part. I can write it like this. Now you know that these two things are disjoint. I can use additivity theorem. So I can say probability of E is equal to probability of E and F plus probability of E F complement. Okay, this I can clearly write. So probability of E. Now this is given to me. Okay, this thing is given to me. So I can substitute these values directly. I can say this is probability of E multiplied by probability of, this is plus probability of F complement. Okay. Now because this is my goal, this is what I have to prove. I have to see if this is correct or not. The only substitution that one more substitution that I'll do, I'll take P of E as common from both of these. What I can do is I'll do something of this sort. So I'll take this over here. I'll say P of E F complement is equal to this and this. I'll take P of E common. Let's do this step also so that I don't confuse you. So this is probability of E minus probability of E, probability of F. The probability of E F complement is equal to, take P of E common from both of these, probability of E, 1 minus probability of F. Okay, so what is the probability of F? This is 1 minus probability of F is probability of F complement, probability of multiply probability of F complement. Okay, again that this is what we had to prove, and hence E and F complement. So hence E and F complement. Again going through it. Okay, so what I'm saying is, so once you are given an English statement, so till now we're just looking at how can I read mathematics like poetry, how can I read mathematics in plain English. Now if you are given plain English, how can you convert it into mathematics? I was claiming that if E and F are two events which are independent, then I was saying that E and F complement should also be independent. So I said this is some verbose statement given to me in English, so what I should do is I should first convert this English into mathematics, because both are languages. Mathematics is a language, English is a language. Okay, now I am convert, and English is less expressive than math. In math you can express more than English. So I said, okay, given to me is basically this, because this is what independence means in mathematics. Probability of E and F is equal to probability of E multiplied probability of F. This is basically meaning of independence. And I have to prove this. Probability of E F complement is equal to probability of E multiplied probability of F complement. So I said somehow I should bring this F complement in the picture. Okay, now and I should somehow use this result. So I said we have seen this multiple number of times. I can break them down this E into two different regions which are disjoint, and then I can use additivity theorem. So this is usage of additivity. Okay, here I broke it down into two smaller sections which are completely disjoint, and I use the probability actions, and then I just did some algebra over here. I just moved some things here, some things here, and then I arrived at this is okay. This is how I can prove mathematically. You can also come with the intuitive explanations also now. You can now think, okay, so you see how much power mathematics gives you. You don't have to even think now intuitively. You just perform some algebra and you arrived at some result. So one more thing, that if there was no mathematics, let's suppose if there was no mathematics and somebody told you I have an event E and I have its complement event, let's suppose E complement, and I have another event F. If E and F are independent, and how can you prove that E and F? This becomes too verbose. Even to just carry this in the brain becomes very hard. Then to come with the intuitive explanations is very hard. That's why I said mathematics is a more expressive language, and sometimes you can just move it. It's like somebody is giving you a map. You have to just travel to the map. So once you navigate to the map and you arrive at the right results, if you have done the algebra right, you will arrive at the right results. And without being intuitive, without thinking through these lines, without thinking this is independent, this is dependent, and all sorts of that stuff. That's power of mathematics. Mathematics gives you a more expressive language. So to show you this proof was to show you how can you basically convert English statement into mathematics. This is pretty basic, pretty level 0 stuff, but this is where we build from. So the more we'll go forward, this is the notion will be created. So you'll have a problem in the world which will be given to you in an English statement, or it will be expressed to you in some statement which makes sense in the real world. So then you will have to convert it into mathematical problem, and then you will have to use the rules of mathematics. You will change the game basically. You are bringing it to the mathematical world and using the rules of mathematics to arrive at some result. And then you just have to do one more thing. You have to convert back it into the real world. So here I did the conversion. I said if I prove this, that means it is independent. Any questions on this? So here we saw the independent events. Now let's suppose if we have three events. If we have events E, F, and G. We have three events: event E, event F, and event G. In order to prove their independence, you should not only prove that probability of E, F, G is equal to a probability of E multiplied by probability of F multiplied by probability of G. You should not just prove this, but you should also prove pairwise independence. That means you should also prove that probability of E and F, probability of F and G, probability of E and G. All of these should also be proven as independent. That means probability of E multiplied by probability of F, probability of F multiplied by probability of G. And this can be also extended to an event. If you have to prove something of this sort for three events, so you're first proving this thing. You are saying that three events are independent if this thing if this thing holds, this thing holds, and if this thing holds, and if this thing holds. These four things should hold. They should be pairwise independent. Then they should be, all of them should also be independent. This you should also prove. So let's suppose if you have to do it for n events now, you'll have to prove for 2 events, then 3 events, then 4, then 5, then 6, till n events. So this is how you should prove independence. Sometimes we assume that you can directly extend the definition. If 2 events are independent, you generally use this definition. And if 3 are independent, some people resort by symmetry. They say that this should be the only case that we should prove. But no, you should also prove these things in order to prove that the 3 events are independent. And this also extends to n events. Here I'll leave the proof for you. You can prove it, but first think why is this case, and you can take some examples, think it from that direction first, and then try to formally prove it by using the mathematics. Now why are we focusing so much on independence? Because this independence not only carries value in machine learning, not only carries value in, let's suppose, deep learning, it also has a lot of value when you are performing some real world things. Okay, so in machine learning you might have heard IID. We are taking these samples IID. Okay, we are taking identical and independent. We're taking them independently. So there is one thing that is independence. We're taking the points independent. That is when you are sampling the points, different data points are taken independently. They don't have a dependence. Okay, that's why we'll assume that the sampling is independent. So one more thing is, let's suppose if you are developing a system. If you are developing a system and you are thinking that if I connect these things in series, or if I connect these things, that's where you have hard drives. You have hard drives. You are thinking that let me have 4 hard drives, because I believe that my hard drive this getting corrupt is, let's suppose, 5%. Okay, each hard drive getting corrupt is 5%. Then how many hard drives should I require, so that I should be sure that if the fault happens, I should be very least impacted. Okay, so you use this sort of independence there, because you believe that all of these hard drives are independent of one another. So if something happened in one hard drive, if some error came up in one hard drive, so other hard drive is not impacted by that error. So you do computations of that sort. Okay, let's do a question on this. Let's suppose you have a system. You have a system composed of n separate components. So there are n components in that system. So these components can be, if you are having a network, and there can be a lot of components in a network from a computer science perspective, or if you are running a huge industry, or there can be different components in that industry. Now we have a system which is composed of n components. We have n components in the system, and the system is said to be in parallel, so it can be in series or parallel. It depends how do you connect these things. So we'll do it for series as well as parallel, or we can do in the combination, because that's how usually these components are wired together. So they can be in series, they can be in parallel, or they can be in the combination. And each of the component will have some probability of falling, will have some probability of having some error, or they will be getting affected by something. So you compute this probability, and then you have to compute probability that this system will work. Okay, or what is the probability that this system will not work. So you compute these probabilities, and you accordingly keep the backups. Okay, in order to keep the probability in order to make the probability very high, make your system so that it should not always give me the error. So you connect the component in separate ways. You also have you keep more components in check. Okay, so you do it with the probability. So what I'm saying is there are n components in the system and they're connected in parallel. And now if a system, when at least one component functions, a system is said to be functional. Okay, now we have something of this sort. So you have A, and in this you have some parallel components. So let's call these as components. Okay, and out of these things, then you have this B, something of this sort. You might have seen this in electric current when you were in +1, +2. This is a system in parallel. Okay, system in series is something of this sort. You have something of A and something of B over here. So in both the case, some systems are like this, some systems are in the combination of a series and parallel. So what I'm saying, a system is composed of these n separate components, and it is in the parallel. So if at least one component works here, the whole system works. For such a system, if component I, which is independent of other components, so here if we assume the independence between the components, okay, so each of this we have component 1, component 2, component 3, component 4, and so on. Okay, this can be, let's suppose, n components. The question goes like this. It says that if component I, which is independent of other components, function with probability pi. So with probability pi, they function. Okay, so what is the probability that this system will function? Okay, you have to compute probability system will function. You are given the probability of each component. So let's suppose if given first component works with probability p1, second component works with probability p2, third component works with probability p3, and nth component works with probability pn. If you are given these probabilities, and if system is in parallel, that means if one component works, that means the whole system works. So what is the probability that this system will work? The question asked was, if we have a system with n components, the n components are in parallel. So by parallel, I say that if at least one component is working, whole the system is working. So each of the component, let's suppose this is ith component has probability of working pi. That means if I have first component has probability p1 that it will work. Second component has p2 of probability it will work. This is in series, and this system is in parallel. This system is in parallel. Sorry, this is in parallel, and this is in series. The second system is in series. So in series, a system will work. All the components work. The probability of the component is the same as given for the first system. So now you have to compute what is the probability that system will function, either system 1 or system 2. What was the probability? So in the first case, what I said is, so here you should have at least one of the components should work, then the whole system will work. So whenever I say that, it is easy to think in the complements. I say you should think it like this. You say no component works. No component is basically, if I have A1 means first component fades. A2 means second component fails. So I can write AI. AI means ith component fails. So I am saying that you should compute no component works. That is, everything fails. So when everything fails, that is probability of intersection of AIs. This means probability. What is the probability that every component will fail? And you take a complement 1 minus of this. You are saying that 1 minus probability that every component fails means at least one will work. The probability everything will fail, if you take its complement, that means at least one will work. So you have to compute this. That when at least one will work, that means probability that the first system is functional. Probability first system is functional. Because this is when the system functions. You have to make sure that at least one component should work. So how to compute this now? This is 1 minus. Here you can compute it, you can just multiply these things. 1 goes from 1 to n. Why? Because here we have assumed independence. That each component is independent of others. Now you can compute it 1 minus pi goes from 1 to n, that's multiply. So AI, what is the probability that the first component will not work? The first component will work had a probability pi. The probability of not working will be 1 minus pi. So this is the answer for the first component. First system rather. This is the probability that first system will work. And accordingly, you have to compute the probability that the second system will work. Okay, but now you can also compute what is the probability with how many components. You can fix this n. So you can also come up with the answer n over here. So if you have to come up with the probability, let's suppose if I tell you that I want my probability to be greater than 95%. So you can put the 95% value over here. You can come up with the value of n. And if given the pi, you can say okay, you at least need these number of components. connected in parallel so that your system will be reliable. Your system is having 90% probability it will function. Okay, so these types of problems are everywhere. So as I said, in YouTube, you might have heard that these YouTube, they have placed 7 servers. How have they computed? Because they know the reliability of their server, they know probability of the failing of their servers, and they have used independence, and they will come up with this number n. So how many of the replicates we need? Similarly, if you are deploying any other system, so you have to compute these things, and first you have to compute this. You have to say, okay, what is the probability the system will fail or this system will work? What's the probability of that? And that will depend on which company has manufactured the product. And then you have to ask the questions, when you manufacture the things, how likely is it to fail? Okay, then you come up with numbers and give these assign the probability, and you bring a mathematical notion so that mathematically you are well grounded, at least that I have 95% of probability my system will work, something of this sort. You come up with these numbers. And similarly, when you do the series, question, you will come up with some number, and there you can also find n. Everybody clear with this? Any questions still here?